All right, well, we'll go ahead and get started. What? We'll record everything and make it available on the old YouTube. Did you have any trouble staying caught up on the lectures and stuff? Did you use those YouTube links? Or?
I did not. I was gonna ask you on the Google Drive, then we did it that one day in class. Where do I go to in that? I started to one day on my laptop home.
So if you go to on your Google Drive, when you open it up, over here on the left, if you click this shared with me, you'll see a folder that looks like this, like this 133
Yeah, I
shared
remember
folder.
that.
And then you double click on that, and there's a formula sheet, copy of the Zoom recordings, the syllabus. If you click on the Zoom recordings, it's all these links for recordings that we've made.
Okay.
There was none this past Thursday.
Okay. So, and getting on the drive itself, where, I mean, I know it's simple. So,
Yeah, if you go to Google and just search for Google Drive,
okay, just Google, okay. I thought,
click on Drive, and then for me, I'm already logged in,
right.
but you put your atlab.icc.edu account in there, and it'll open. When you open it, it'll look something like this. I use Google Drive for everything, so I got a ton of crap on there.
Okay.
But yours, you'll see that folder on the left that says shared with me. All right, true or false? A 90-degree phase shift between capacitive voltage and capacitive current is true in any sine wave circuit. True. This stuff that I put on the right, this is straight off. It's off of your formula sheet, and it's also, I pulled these pictures straight out of the book. So, but that phase shift is indicated in both these two pictures. So on the right hand side, if these were in a resistive circuit, if capacitive voltage and current were in phase, it would look like this, right? It's indicated like in a purely resistive circuit on the first page.
Okay, and then with the resistance, they share a point, right? The capacity they want to make.
Well, this is a resistive circuit, and you can see how current and voltage are in phase with each other. You have a capacitor in series with an alternating voltage source. The current tends to lead the voltage, meaning the peak of the current is 90 degrees in front of the voltage. And that has to do with capacitive reactance. And then with the phasor, here's the phasors over here, and that shows you that if capacitive current is 0, and we're going 360 degrees in a clockwise direction, voltage is negative 90 degrees in relation to that. A coupling capacitor is used to pass the desired AC signal variations while blocking the steady DC level of a fluctuating DC voltage. Although capacitive voltage lags capacitive current by 90 degrees, both waves have the same frequency. False?
The frequency is the same.
That's true.
Okay, yeah.
Right. Frequency is how many times does it cycle per minute, right?
Oh, okay.
Or per second.
Yeah, my brain was thinking something else on it.
Capacitive current is the same in all parts of a series circuit.
True.
That's true. In a series circuit, there's only one path and current will be the same through all series connected components. If capacitance is increased and higher frequency sine wave voltages are applied, what happens to capacitive reactance? Decreases. So let's take a look at that in the formula. If capacitance is increased, so if we take this and increase it, and higher frequency sine wave voltages are applied, so if we take this and increase, what happens to capacitive reactance? It must go down because capacitive reactance, X sub C, is inversely proportional to all this stuff, right? That's why it's 1 over all that stuff. So if you plug some numbers in here, like frequency was 1 and capacitance was 1, so 1 over 1 over 2 pi 1, 1, that would be 1 over 2 pi, right? If we increase the frequency and the capacitance, you'd get 1 over, let's say we'll just bump it from 1 to 2. 1 over 2 pi 2, 2. 2, 4, 6 pi. So 1 over freaking calculator. 1 divided by 2. Times pi. Where's pi? Where's pi? This is 0.159. And if we increase frequency and capacitance, we have 1 over 6 pi. This would be 0.053. So capacitive reactance has gone down, right? In a series circuit, in a series RC circuit, which means a resistor and a capacitor in series, resistive voltage and current are in phase, out of phase by 45, 90. Which one is it? They are in phase. Yep. The applied voltage in a resistive capacitive circuit is always in phase with the current. In a series RC circuit, the phasor for capacitive reactance, what is IXC? Oh, What does IXC mean? Passive current, is that X supposed to be there? Is that a typo? In a series RC circuit, the phasor for X sub C, IX sub C. What capacitive voltage is at. I'm not sure what that means. You guys understand that question?
I remember finding the answer in the book, that's what I was looking for. I think it's word right. I don't know.
Yeah, I think it was, and I know how to do it. Okay,
Yeah, page 285. Triangle.
Computer's slow this morning.
Two
285 is number 2 in the list of summarizing similar phase triangles.
Nothing else, just light voltage, 141 voltage, the pipe, the color. The 141 off, the 51, and then the cooling. Yes, it's higher voltage, 1 time, 10 times the or 100 voltage. The IXC voltage is 1 amp, like 1.
You know, the first question,
Yeah.
I didn't see the book, I knew the answer.
The answer, yeah, the answer is in the question too, right? On 285, the answer is,
You know, right hand column.
yeah, and the number
Right
2,
there, number 2.
right in top, yeah.
Yeah, phasor for X sub C, IX sub C, or V. C is at minus 90 degrees. Okay, so it's talking about the phasors. Don't remember the wording of that question. Oh, I remember now. Impedance Z triangle. Okay, so you will have questions like this too to solve for impedance. Remember, impedance is a fancy word for resistance, but it's resistance in an AC circuit. So in a DC circuit, well, you have resistance in an AC circuit too, if it's a purely resistive circuit. But if you have things like capacitors or inductors in an alternating current voltage circuit, you have impedance. And impedance is either more or less than the total resistance of the circuit. If you put the phasors together, so this is like this is like physics stuff. But impedance, the Z sub T, total impedance in a circuit, a circuit with a capacitor and a resistor in series is equal to this formula. And that should be on your formula sheet, is it? It should be on there. You should have a page that's all about capacitors right here. X sub C and R in series. And this formula sheet is handy because if you have this this scenario where you have a resistor and a capacitor in series, right in the picture. So you got alternating voltage, so current's going back and forth. You have a resistor and you have a capacitor in series with each other. This is what everything looks like. Your phasors are right here. Your resistance, your resistive voltage, your resistive current, your capacitive current, and your total current are all in phase with this zero line. Capacitive reactance and capacitive voltage are 90 degrees out of phase, and your impedance is solved by putting those phasors in a triangle. It's this long phasor right here at a diagonal. So in regards to the question in a series RC circuit, the phasor for X sub C, capacitive reactant current, or capacitive voltage is at 90 degrees, negative 90 degrees. So that would be this phasor here, capacitive reactance, capacitive voltage. It does not show on there capacitive reactant current. Which to me that X should not be there. It's just, well, I guess it, yeah.
So that means capacitor reaction, no, okay, ISP means ampere, ampere,
Yeah, I is current. So current as a result of capacitive reactance is how I would say that.
and one, I think here, one, A means ampere, right?
Ask that again.
One, and letter A, capital A, means ampere, right?
Yeah,
A, it wasn't A, symbol for ampere.
yeah. But I in Ohm's law also means current, right?
Yeah.
So current amps, I, A, however you want to put it, it's
Yeah.
current. Let me zoom in on this a little bit. So if you were going to find impedance in a circuit that had a resistor and a capacitor in series, here's how you would find it. This tip to tail method, where let's show Z sub T, resistance, there it is. So this is impedance. Z sub T means impedance. That formula is square root of R squared plus capacitive reactance squared. Where do you think they got that formula? It's the Pythagorean theorem. Remember the Pythagorean theorem? A squared plus B squared equals C squared from a triangle. Come on, man. All right. So remember this whole page on your formula sheet is a capacitor and a resistor in series. So it's as if we put a resistor up here in series with this capacitor. This is what the phasors for that would look like. So your resistive all right, I'm just going to use this triangle. So your resistance is in phase, right? So this would be 0 degrees. And your capacitive reactance is 90 degrees out of phase, right? So the total, you were going to add two phasors. Remember, phasors have a magnitude and a direction. If you were going to try to find the total of that, you would use what's called the tip to tail method. So we're basically taking this phasor and moving it over here. That looks like this. Then you can solve for a triangle. In a triangle, Pythagorean theorem says a squared plus b squared equals c squared. That means the two sides you're trying to find. Remember what this dotted line is called? The hypotenuse. If we replace a and b with r and x sub c, you get this is impedance, right? So it's the total between the two. Z sub t equals r squared this squared equals r squared plus x sub c squared. If you take the square root of both sides, that cancels and that cancels. And what you're left with is total impedance equals square root of r squared plus x sub c squared. So they're using phasors and the laws of triangles to solve for total impedance, and that's how they get this formula, right? Total impedance equals the square root of r squared plus x sub c squared. That makes sense? In series circuits, the current I sub c, so capacitive current is the reference. Then the voltage, capacitive voltage, can be considered to lag capacitive current by 90 degrees. Is that true or false? True. Let's look on your formula sheet. Because you have the best instructor on the planet, you're given a formula sheet that has all this crap on it, so you can use it on the quiz. Whoop, whoop. So what does that question ask? In a series circuit, the current is the reference. Okay, there's capacitive current. See it there. And the voltage, capacitive voltage, can be considered to lag that by 90 degrees. Is that true? Yep, look, it's right down there. Minus 90 degrees. The 90 degrees phase angle, where'd you go? Results because capacitive current depends on the rate of change of capacitive voltage. That's true. If you remember from last week, we talked about this a little bit, but on your formula sheet. I really need to make this so you're, holy crap. In a capacitive circuit, where break this over so I can draw. Where capacitive current is at its peak, right here. So this is the maximum current at this point in time. The rate of change, so basically the slope of the voltage is at its maximum, right?
Yeah.
At this point in time, the rate of change or the slope looks something like this. It's extreme, but it's not as, the rate of change is not as much. I don't know how else to say it, as the rate of change at this point right here. So that's what it's saying. The current is maximum where the rate of change of the voltage is at its maximum. What is the rate of change of the voltage right here at its peak? What's the slope of that line? What is the slope of this line? At this point in time, how much is voltage changing? Zero. Do you notice that the slope of that line is zero and the current at that point is also zero? Because the rate of change of voltage at that point is zero. At this point, the rate of change of voltage is at its maximum in the other direction. The slope is most extreme at that point in time. And it's also the maximum current in that direction. You see that? So that's what that question is saying. The current is at its maximum where the voltage at the capacitor is changing at the most maximum rate. You have to really dial down to a specific point in time on the sine wave. That's what the question is asking. The opposition that resistance offers remains the same for DC and AC circuits. Is that true or false? That's true. Because a resistor doesn't care if it's AC or DC. The resultant phasor addition of capacitive reactance and resistance is their total opposition in ohms, and that fancy word is called impedance. The trigonometric function, everybody say that. I love that word. Say that with me on the count of three.
That's like a function.
Trigonometric, you ready? You say it really loud. This is going on YouTube. Ready? 1, 2, 3. Trigonometric. Lewis is like, hell no, I'm not saying that word. Of an angle equal to the ratio of the opposite side to the adjacent side of a triangle is tangent. That is where we get the formula for the phase angle. That's where we get the formula for the phase angle right here. So in this circuit, capacitor and resistor in series, there's a difference in the phases, right? So in this case, the phase shift is minus 90 degrees. This angle here, theta z, so the impedance is equal to the inverse tangent. No. Tangent of the angle is equal to minus x sub c divided by r. This is trig stuff. I don't know how much trig stuff you guys have learned in the past, but you remember SOHCAHTOA from high school? No? Well, here it is. My amazing handwriting. So, this is trig laws of a triangle. So in a triangle, in a right triangle, you're talking about these angles. So if I pick an angle right here, let's call this theta, that is equal to, where's the hypotenuse of this triangle? The hypotenuse is always opposite of the 90 degree, right? So this is hypotenuse. So if I wanted to know what, if this is opposite and this is adjacent. So relative to this angle, you have a hypotenuse, an opposite, and an adjacent. The sine of that angle equals opposite over hypotenuse. The cosine of the angle equals, I should put the angle in there, equals adjacent over hypotenuse. The tangent of the angle equals opposite over adjacent. So in this triangle, if we're trying to find theta z, and what we are given is the opposite, which is capacitive reactance, and the adjacent, which is the resistance, the tangent of that angle equals opposite over adjacent. That's where this formula comes from. Does that make sense? We'll do examples of all of this. We're going to solve, in this chapter, we're going to solve circuits using a shit ton of math. So just stay with me and I'll walk you through it, how I solve them, how I use the formula sheet to solve them. And we'll do as many examples as you guys want to till you feel comfortable enough to take the quiz. Anyway, the trig and the math, I'm just showing you this stuff to reinforce where all these formulas are coming from. So maybe it helps it to sink in a little better. What circuit has different branch currents, but one common voltage? Let me reword the question. What kind of circuit has the same voltage throughout, but on each branch, the current is different? Parallel. What is the component called that is used to pass AC signals to the load resistor while blocking low frequency in DC? Coupling capacitor. What is the total current when 30 milliamps resistive current is in parallel with another branch of current of 40 milliamps for capacitive current? 50 milliamps. How do you solve that?
of it.
That's the same as,
Each one divided by one. They might just add-
the reciprocal formula. Yeah. And since there's only two, you can also use product sum. Either way you strike it. So, so what is that saying? Basically, we have a parallel circuit. And we have 30 milliamps resistive current. And we have 40 milliamps capacitive current. This would be I sub R, current through the resistor. And we have 40 milliamps capacitive current. Product sum method, so it's asking for total current. The product sum formula is 30 times 40 divided by divided by 30 plus 40 equals 50 milliamps. When resistance and capacitive reactance are in series, current and IR, so what does IR mean? Voltage. When it says IR, that means voltage because E equals I times R. V equals I times R, that's Ohm's law. I don't know why they don't just say voltage, but they want you to think about it, I guess. When resistance and capacitive reactance are in series, current and voltage have a phase shift of resistance and capacitive reactance are in series. What is the question now? Current and voltage? Okay, so here's your current, resistive current, capacitive current, and your voltage across the resistor though. IR, okay. I wonder if that's in the question, it's supposed to be I sub R. Anyway, the phase shift is 0 degrees. Anybody remember seeing that question in the book? The question is when R and X sub C are in series, I and IR have a phase shift of, and the answer is 0 degrees. I and IR.
Yeah, then put the I sub R,
Where do you see that? Oh, current through, oh,
Number 4.
I through R, and it's IR voltage drop are in phase. Therefore, I and IR have a phase angle of 0 degrees. Okay, I just wish it was on the formula sheet more specifically like that. So this means resistive current. But it doesn't say IR, like the voltage drop across the resistor. So you're just gonna have to remember that one. It's not on your formula sheet. When R and X sub C are in series, the current through X sub C must lead the voltage, the current through capacitive reactance must lead capacitive voltage by how much?
What question you have, Marie?
Basically, yeah. When a capacitor and a resistor are connected in series, the current is the same in both X sub C and R. True. When analyzing an RC circuit, which of the following values of I and V can be used?
All 3.
Yep. It's a dumb question. When branch currents that are out of phase are combined, branch currents. So we did an example over here. Are they simply added? Are they simply subtracted? Are they added taking phase difference into account? Or is the resultant 0? Correct. When capacitors are connected in series across a voltage source, the series capacitors serve as coupling capacitor network, voltage divider, filter, or voltage tripler. Yeah, be a voltage divider. Yeah, the same as using a resistor across the voltage source, right? You're using that capacitive reactance or the resistance as a voltage divider. Voltages are out of phase. Man, these questions hurt my brain. Voltages are out of phase. Rhythmic addition, blah, 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 blah. Phasor addition isn't necessary. If they're out of phase,
The question is not possible.
phasor addition is necessary. Think of it this way. Are these two in phase? The black and the blue, are they out of phase? I got a smaller voltage and I got a bigger voltage. Both starting from the same point. Are they in phase or out of phase? They're in phase. If they're out of phase, phasor addition is necessary. Should draw it like this, so it's 90 degrees. Easier example. So if they're out of phase, we have to use this tip to tail method. Your total is this dotted line. On a sine wave, here's what it looks like. Small voltage. Big voltage. But they're out of phase. To add those up, we use this tip to tail method and we find this total right here. Another way to look at this is if this total, let's say, is 3 volts, and this total is 5 volts, and we wanted to find the total of both of them, could we just say, hey, yeah, it's 8 volts? No. The resultant sine wave is somewhere, some kind of an average of those two different sine waves. It looks something like this. It's somewhere in between there, and it's not 8, it's somewhere between the total of 8 and 5, right? You are adding them, but they're out of phase, so you're not getting as much. So in other words, if this was 5 and this was 3, how could we find this in a triangle? Pythagorean theorem, right? So 3 squared plus 5 squared. Call this t for total. T equals the square root of 3 squared plus 5 squared. Somebody do that for me real quick. What does that equal? Like 7, somewhere around 7.
Five.
5.8. That's what I said. Yeah, 5.8. That's a good guess, Zach. Thanks. All right, 5.8. So this total right here is 5.8. It's not 8. It's not 5. It's this weird 90 degrees phase shift total. This is also illustrated on your formula sheet. In this example. This kind of brings everything together, and there's a lot of information on this one little graph, but I wanted to point it out to you because 2 years ago, I went to a lot of effort to put this thing together to help you visualize it all, because I'm a visual learner. But let me see if I can put this over here. So the left and right side of the screen are the same thing, but oh wow, I just did, that's weird that I picked the same numbers, 3 and 5. Okay. So if I have a resistive peak here, represented by the red line, 3 volts, and I have a capacitive peak here, 5 volts, the total is not up here at 8, right? This would be 8 somewhere up here. The total is this 5.8. You see how they're 90 degrees out of phase though? From this point to this point, the peaks are 90 degrees out of phase. See that or no?
Mm-hmm.
I know there's a lot of information here. I know it's confusing, but if you follow me, this helps you visualize it all. This difference in the total is the phase angle, theta V. So if a question asks you, what is the phase shift between of the total voltage, you could find this tangent theta V equals negative VC divided by VR. And that's all has to do with those phasor triangles. So all these formulas and all this crap that's being thrown at you, this is where it's coming from. And the formula itself is pulled right out of the book. It's on your formula sheet, but this picture kind of helps illustrate for you where it's coming from. The difference in the peaks, we can't just add them together. Because of the phase shift, we can't just add them together. They're a weird average total. That's found by using the phasors and the trig. That's where those formulas come from. And then if you wanted to find where this peak was at, let me ask you this. In purple, this peak, do you think it's closer to the black peak or this gray peak down here?
Cycle. Or
Yep, this peak, this purple peak right here.
it looks like it's directly 50-50.
Sort of, yeah, I mean, but it's actually way closer to this one because it's bigger, right? So this phase angle here is not gonna be 45 degrees, right? It's gonna be, I don't know, 70, somewhere around there. It's closer to this peak because it's this one's bigger. If the resistance voltage had a bigger peak, that angle would be closer to it, but want to point that out to you. Phasor dish is necessary, is that what it's saying? All right, 23, with sine wave alternating current, the voltage division between series capacitors can be calculated on the basis of reactance. The last one. Oh, thank God. Going through all that help at all? Sure hope so. Now here's the kicker. Let me give you a little information that might help you on the quiz. Look at all the true false questions. There's one. There's one. There's another 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 one. Do you notice anything about all of them? The reason for that is because I think it's hard with a subject that's as confusing as this, when I pick the questions out of the pool, to ask you guys a question, blah, 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 with a bunch of 5-syllable words in it, and have it be false and make you think about that. Like, that's just more confusing than anything else. So that's just a little tip for you who decided to show up today. Ready? Thank you, Zach. Yeah, you're welcome. I know you love me. For the quiz, though, let's see if we can make this even more difficult. Hmm. So of all those, really fun questions, there's 6 multiple choice. And then they're gonna have you solve some circuits. We're gonna have to spend a bunch of time going through these until you guys are comfortable enough, so we won't do a lab today. Let's take a little break. And we'll go through some examples of solving a series circuit, solving a parallel circuit, because on your quiz, that's what you're gonna have to do. We're gonna take about 5 minutes. No, so Thursday, remember we had that weird, you were upstairs, we had that weird stuff going on. It was just kind of a lab day for those that came in. So we didn't get a chance to go over the homework until today. So this morning we decided, well, let's go through the homework and then we'll make a decision. So I'm thinking when you see the way we're gonna have to solve these, you might want a little time to practice. Thursday. And keep in mind that you also have homework due on Thursday. So I can push that back as well. I'm happy to do all that. I want you guys to be able to comprehend this stuff as best you can. All it's going to do is later chapters we're going to squeeze into the last couple weeks. We are about a month away from being done, which is fine with me because the later chapters, like all this math, all this stuff with capacitors, we're going to do the exact same thing with inductors, and it's a whole new set of rules, right? Those are the 2 big areas that we have to get through, and then there will be some chapters on a little bit of like transformers and power generation and distribution, all good stuff, but this stuff takes a lot of time. So why don't we plan on quiz Thursday? Homework will be due the following Tuesday. Sound good? Well, where's that? Whoa. Freaking. Chapter 18 homework, we're gonna move that to next Tuesday. Chapter 17 quiz we'll take Thursday morning. Sound good? Who's excited? Who loves AC circuits?
I do.
Me and Joe, we're the only ones, but hey,
I have no reason to.
yeah. Why do you think you guys are learning all this? Joe has already found some practical applications of this stuff,
And I have to for work.
and he has to for work too.
Before I had to do my 2-week thing here, I wire up 2 3-phase motors.
Yeah,
And, make sure it turns things in the right direction.
yeah, and motors are basically a big inductor, right? Big giant winding transformers, right? That's all inductance. We haven't even talked about inductance yet, but
That'd be a reason.
let me jump the gun and say, okay, you haven't even talked about inductance and inductors yet. What do you think if a phase shift for a capacitor is negative 90 degrees, the phase shift for inductor just happens to be plus 90 degrees. So when you have all this reactance and stuff happening, might give you some bad juju happening, like there's things called resonant frequency, where a sine wave's amplitude is at its maximum, when capacitance and inductance are at a certain frequency. So basically what ends up happening is you use capacitors or inductors to counteract capacitance, or you use capacitors to counteract inductance. There's also something called filters. So if anybody have, well, a power supply, your power supply has filters in it. Power supply takes big AC voltage and drops it down to smaller DC voltage. You guys probably all have inverters in your vehicles, right? That takes a smaller DC voltage and turns it to a bigger AC. You use things like capacitors, inductors to make that happen. If I wanted to take an AC sine wave, right? AC, you see what I'm doing here? Alternating current, up and down, back and forth, right? And what if I wanted to make that a DC 12 volts? So I can charge my battery on my truck. You would use basically a big power supply, right? A big one of what you got in front of you with things called capacitors in them. So if capacitors block direction of current flow in one direction, what does this turn into? It turns into this. Now it's direct current. It's really variable, doing like stuff like this, but it's not letting this happen anymore, right? Capacitors have blocked the one direction. So now you have this, and we can use filters, which are capacitors, inductors, certain sizes, to kind of make it do that instead. And you can fine tune it till it looks like that, right? There's your 12 volts.
Half wave or full wave.
Yeah, rectification.
I'm blowing up a few.
Yeah. Yeah, and if, I promise you this, if you all pass this class, now the pressure's on. We will blow some shit up in here. Because I know this is not fun, but it is important. That being said, I wanted to take a break for a reason. That reason is that I really need to poop. Can I go poop now? I should have paused the recording so I didn't say that online, but it's okay.
It's not in here.
Yeah, you might, I'll go to the bathroom first, I promise. Okay, 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 okay. Okay. So you're going to be given two types of circuits, one at a time. First, let's solve for a series circuit. Series RC circuit. Let's call this 50 volts AC, and let's call this 40 kilohertz. And let's call this 4 kilo ohms, and let's call this 5 nanofarads. And it's going to ask you to solve for everything.
That 40,
40 kilohertz. It'd be helpful if I took over your screen. What do you see? So I can do this, but it won't be on the projector. Yeah, I gotta change the recording. You have your, you do have your computer screen or mine?
I have mine.
How about now? What do you see?
It's up to now.
You see the circuit?
Right.
Okay.
Yeah, you got logged in.
How late does this class go till noon? All right, you logged in? Man. Mouse doesn't work? Huh?
Don't know how.
People right. What? You said, I make your life what? I make your life what? Stressful? Good. Okay. In any circuit, we should be able to solve for total current voltage and resistance, resistive current voltage and resistance, capacitive current voltage and resistance. So this is your resistor. This is your capacitor, correct? So what I like to do is I just like to write everything down that we're gonna have to solve for. And on your quiz, you're gonna get a question with a picture of a circuit, and then it's gonna say, what is the total voltage in the circuit? And then the next question is gonna be, what is the voltage across the capacitor in the question, the circuit in question, whatever. So if you just, in the first question, write everything down, solve for everything, and then go through and put your answers in, that's what I would suggest you do. Okay, so total voltage, total current. And what is the total resistance in an AC circuit called? Not resistance, it's a fancy word. Impedance. What's the symbol for impedance? What? Z. So total voltage, total resistance, total voltage, total current, total resistance. Can we solve for the voltage across the resistor? IR. What is the resistance of the resistor? That's just R. Voltage across the capacitor. Current through the capacitor. And what is the resistance value of the capacitor? Is it R? Z is impedance. But the capacitor is doing something to that circuit. Yep, capacitive reactance. Remember, that's an ohmic value. All right, so is there anything straight away that we can solve for? We're given total voltage, right? We're given resistance. Are you logged in? You were logged in? Are you logged in now? Are you logged in? If you're sitting there, log in real quick. And let me know when everybody's logged in. Everybody logged in? Everybody see what I'm seeing? Okay, is there anything else now that we can solve for? What's the first thing we can solve for? Do we have everything we need to solve for current?
Oh, yeah. Yeah, we have a few things that we can
You can solve for the current at the resistor? How do you know what the voltage drop is across the resistor? You're gonna get total voltage across that resistor? Nope. What about this little formula? Can we solve for this?
Yeah, yeah.
We have enough information to do that, don't we?
Yeah.
What is that? 40,000. Times 0.0005 nano. So be 0.00005. You can do it like this, like me, or you can do it with all the e's and to the powers and however you're most comfortable doing it. One divided by parentheses 2 times 5 times 40,000.
What's 40,000?
What's the frequency F in the formula?
Okay, okay. Yeah. What's 40,000?
Times 0.000000005 equals 795.77 ohms. $795.77. Now what can we solve for? What can we solve for now? We have two resistance values. Maybe we could solve for impedance. Well, let's look at the old formula sheet. What does it have to offer us? If I'm you, I'm looking at this page because it says, hey, capacitive reactance and resistance in series. Can we solve for total resistance or impedance? Yeah, we sure can because we have a resistance value and we have a capacitive reactance value. This formula is derived using the triangle below, but we don't really care. We have a formula, so we're happy. Z of T equals the square root of R squared plus X sub C squared. So the square root of 4,000 squared plus 795.77 squared. So if I hit that, That gives me the square of 795.77. If I add that to 4,000 squared equals, I have 1 divided by or, oh no, I have to just take the square root, right? Where's that at? You need me to answer it? There is your total impedance, 4078.39. Cool. Now what can we solve for? Corey? You said it earlier. Yeah. With what formula? We have voltage, resistance, and we have it's Ohm's law, right? Because this is a voltage, this is a current, this is a resistance. So E equals I times R, I equals E over R. So using Ohm's law, we can say I total equals E total over Z total. 50 divided by 4078.39. $12 milliamps. Now what can we do with that information? Yeah, I have to look at the question and what it asks for. The question might say I total equals how many milliamps? If it says how many milliamps, you better put 12, and then you better round to 2 decimals. So the rule of thumb for my quizzes is 2 decimals. Okay, so if that's the case, for that answer, I would put 12.26, right? And if you screw that up and you put, hey, I got this wrong because I put 0.012, I'm gonna know you got the right answer and I'll fix it. But pay attention to what the question asks for and try to answer accordingly. Okay, so what can we do with that information? I'll sit here and open a monster until somebody tells me what to do with that information. Look at what we have left to solve. Do we have enough information to solve for that? Bingo, it's a series circuit. Which means that, yeah, which means that IR equals 0.012 amps and IC equals 0.012 amps. Now we can use Ohm's law to solve for both of these, right? E equals I times R. So resistive voltage equals current through the resistor times the resistance. And voltage across the capacitor equals current through the capacitor times capacitive reactance. So that times 4,000 gives you 49.04 volts. .55 volts. We solved for the whole darn thing. Isn't that cool? Now, what do you notice about you add these two up? More than 50. Why is that? Because of the phase shift. Cool. All right. What'd you say? I sub C right here.
Yeah.
It's the same as this, and it's the same as this. Correct. Okay. So I just wanted to show you something real quick. You see on your formula sheet under total voltage, this formula here. Let's double check ourselves, shall we? If total voltage equals the square root of voltage across the resistor squared plus voltage across the capacitor squared, if I took 9.55 squared plus 49.04 squared, when I take the square root of that, I get 49.96, which equals the total voltage. Cool? Good way to double check yourself. All right. Shall we do a capacitor and resistor in parallel? Ooh.
For the value of ER, 0.01.
What did you say? For the value of what?
Our value is
Mm-hmm.
49.04.
Yeah, why is that? Did you take 0.012
Yeah.
times 4,000?
I thought it was 48.
Oh, yep, me too.
And,
Why is that? Because what I did in the example, I didn't round it to 0.012. I had all the rest of it. Let's see. Anybody else do that?
yeah, I just want.
Okay, so it would probably be helpful if you wrote out more numbers. So how did we get the 0.012? We took 50 divided by 4078.39 equals. So you took 0.012 times 4,000. I took 0.01225973997 blah, 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 blah. And that's what gave us different values.
So am I right? If I just like.
Let me put it this way, the more decimals you put in there, the more accurate it's gonna be. That being said, on Blackboard, on the test, when you write in your answer, there's a tolerance there that's put in by me to judge whether or not you're accurate. So if you fall just outside of that tolerance because of something like you just did, if you just tell me, hey, I missed this, but I did it right, I'll be able to tell by your answer that you did it right and I'll correct it. Okay? But your numbers should be close to what we're coming up with here. You know what I mean? All right. Let's do can't keep my eyes off of you. I really love your boobs. Who said that? Let's do 70 volts. Let's do 10 kilohertz. Let's do 2.3 K ohms. And let's do 30 nanofarads. Calm down, Lewis. So I'll wait for Lewis to draw his circuit. Can you sing for him? Do, 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 do. Do, 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 do. Do, 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 do. 2.3 K ohms. Thirty nanofarads. Step one, write everything down. Total voltage, total current. What is total resistance in this circuit called? Starts with an I and rhymes with Schmimpedance. Voltage across the resistor. voltage across, current across, current through the resistor and resistor, voltage across the capacitor, current through the capacitor. And what is the resistive value of the capacitor in this circuit? What do we call that? Tegan? What do we call that? The resistive value of the capacitor in the circuit. Starts with a C and rhymes with capacitive reactance. Capacitive reactance. What? What is it? Yeah, there it is. What's the symbol for that? Starts with an X and rhymes with Schmeck sub C. Yep. Capacitive reactance. Okay, what can we fill out first? Right away, right yonder. Yep, 70 volts. Parallel circuit, so the voltage across each branch is going to be the same, correct? What the French toast? Anything else we can put down right away? Yep. 2,300 ohms. Now what can we do? You can use Ohm's law to find current through the resistor, correct? $70 divided by 2,300. $30 milliamps. I'm going to do myself a solid and write down a bunch of decimals. 304. Three, 4, 7, 8. What can we figure out now? We sure can. We have enough information to do that, right? One divided by 2 times pi times 10,000 times 0.00. Two pi times 10,000 times 0.00000003. 30 nanofarads. What does that give us? Say that again?
0.0018845. Oh, that's not the answer. Sorry, that's gonna be divided by 1,
Oh,
or 1 divided by that number.
1 divided by that, all that check, right? Why don't I just do it? I understand what you're saying. 1 divided by parentheses 2 times pi times 10,000 times 0.0000003, right parentheses, equals 530.52 ohms. Thought that sounded a little small. 530.52 ohms.
So why you got 3? So you put 3 because you want to use the series, right? Instead of 30, another part.
Correct. I don't care how you do it, whatever you're most comfortable with.
Yes, I try to make sure I got the same number.
Right. Right. I did 0.000000003.
Wait, 530,
530.52. Is that what everybody else is getting?
530.51. So
Good enough. All right. Current through the capacitor. Can we do that? Ohm's law, right? IC equals I equals E over R. Hundred and 32 millionths. But I'm going to do myself a solid, and I'm going to say 0.132. Oh, 31946. Now what can we solve for? Maybe we should look at X sub C and R in parallel on our formula sheet. What does it say for total current? Well, it says we can use this formula right here. Square root of IR squared plus IC squared. We solve for the impedance. Yep, we can use Ohm's law for that as soon as we're done with the other one. So first things first, I total equals IR squared, square root of my words are fumbling, so I'll put it on here. Boom. I total equals, that's really hard to read, but why don't I write it out for you? I total equals square root of square root of 0.030434778 squared plus 0.131946 squared. So if I took, I've already got the second number in my calculator already, so I'm just gonna hit squared plus 0.0304. What was I doing? 3478? Squared equals square root 0.13541 amps. Do you all get the same answer?
I got 135,388.
Right, but if it asks for milliamps, I would put 135.41. Right? When I write things down here, when I'm solving, I like to keep all the units in volts, amps, and ohms, which is right. I write the decimals out. My brain gets too confused when I see pico, nani, milli, mega, kilo all over the place. You know what I mean? So I keep all the units the same. That's just what I do. You do whatever whatever makes your little heart happy. 0.13541. That would be amps. Z total. Can we use Ohm's law? Let's look at the formula sheet. Yep, we sure can. Ohm's law equals volts total divided by amps total. So this would be 70 divided by 0.13541, which equals 516.95. Yay. So that's an example of a parallel RC circuit. We did an example of a series RC circuit. Anybody have any questions? So here's what I propose we do. On Thursday, you'll have a choice 9 o'clock when we start. Yes, Zach, I would like to do another example of series. Yes, Zach, I would also like to do another example of parallel before we take the quiz, or let's just do it, take the quiz. So on the quiz, you have yeah, let me finish my thought first, and then I'll go back. You have 6 multiple choice questions, and then you'll have to solve a series circuit and a parallel circuit. Okay. Would it be helpful if I printed those 2 examples out for you? You cannot use that on the quiz, though. You can use your formula sheet, your Uglies book. That's it. Calculator, but it's not a smartphone, right? I would, unless you're really good at long division. I'll bring an abacus just in case you forget. Got it? Louis?
Yeah.
All right, let me know when you're done because people can't log out until I give them their computers back.
I'm on, yeah.
What? Why are you yelling at me? Crap. Grab one of those and see if it printed on, did it print 10 of them or did it print double-sided? Good, yeah. So up at the front on the printer, if you'd like to take one, should be an example of each of the problems that we just did. And once Louis is done, I'll give you your computers back and we'll call it a day. And you're gonna come in at 9 tomorrow?
Yeah.
Okay.
Upstairs.
Yep, AIT 217. What labs do you need to do?
Well, the first lab that we started, I don't think I finished.
14A,
Yeah.
14B.
I don't know, yeah, whatever we have set until today that, for the lab.
So I'm gonna give you 16 as well. We're not done with 16 yet. Done with- If you're not, there's a, I'm gonna give control back. There's a, everything's up on the printer there, so grab what you need.